In this video, we solve problem 15.6.024 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to evaluate the surface integral of a scalar function of x, y, and z, and we're told that the scalar function of x, y, and z is x squared plus y squared plus z squared, and the surface is the right circular cylinder whose axis happens to be the z-axis. It's a right circular cylinder of radius 6, and it's just a portion of that, and it's the portion where x is between 0 and 6 inclusive, and z is between 0 and x. Now, this is hard to visualize. I feel like I can visualize it in my head, but it's really hard to graph on paper. This first part is telling us that we're dealing with a cylinder of radius 6 centered at the origin. And the xy plane, that's going to look like this. So there's my y, there's my x, and that is my cylinder approximately. But z is free to be anything, so this cylinder is coming up out of the page. But we actually aren't interested in the whole cylinder, we're just interested in the part of the cylinder, whereas x is between 0 and 6. So that means we're just interested in this right half. Or when we graph it over here, where the x-axis is sort of coming out of the page at us, and the y-axis is to our right, and the z-axis is pointing straight up, it's going to be the part of the cylinder that's closest to us. It's going to be this half over here. So y ranges from -6 to 6. X goes from 0 to 6. And we're just seeing half of that cylinder. Now, if z also went from 0 to 6, it would look something like this. I'd have an edge of my surface over here. And then I'm trying to draw the exact same cylinder up here. So that would be my surface. But z doesn't range from 0 to 6. Z ranges from 0 to x. So we have to imagine taking this cylinder and intersecting it with a plane, and that plane is given by the equation z equals x. And we know that z is between 0 and x. So if this is the z-axis, and since I'm in a right-handed coordinate system, rather than writing my x-axis or drawing my x-axis on the far right, I'm going to label my positive x-axis on the left. So what we're going to see is the line z equals x, which would look like this if our positive x-axis is over here on the left. And the z values are in between this line, that's z equals 0, and this line where z is equal to x. So we're talking about the part of this cylinder that is between the xy plane and the plane given by z equals x. That's hard to visualize over here, but roughly what it's going to look like is it's going to look like this. If I intersect a plane at a 45-degree angle so that I have z equals x right here, if it intersects the cylinder, it's going to kind of look like this. That's what we would see. So you have to imagine a plane intersecting this. And it's hard. It's really hard to visualize this plane. So I'm going to use Calc 3D. I think the guy's name who came up with this Calc 3D, who wrote it, was Paul Seeberger, I think, at Monroe Community College. And Calc 3D is great. You can just go online and graph some surfaces. You have to get used to all the functions that are available. But this is the plane. This is intended to be the plane z equals x, because that's what this is over here. This is a plane z equals x. So even though it doesn't look like it, even though it looks like a line, you say that z is equal to x and y is free to be anything. So this is like a plane that looks like this coming out of the page at us. And it's intersecting with a cylinder. And that's my attempt at trying to draw the intersection between this surface, which is given by x squared plus y squared equals 36. And we're just interested in that forward, or that front part of the surface where x is between 0 and 6. And then we're intersecting that plane z equals x with that. In order to better visualize this, I'm going to show you how I graphed this in Calc Plot 3D, and then we'll come back to this and actually evaluate the integral that we were asked to evaluate. So I hope you can see now what I was trying to get at. Here's my x-axis. My z-axis is going straight up. My y-axis is over here. I have graphed the relation, otherwise known as an implicit surface, x squared plus y squared equals 36. I just selected this from the list, graph implicit surface, and then it gives you the option to type this in, and then also to list some bounds for x, y, and z, which I already did when I created this one down here, so I don't need this one. Then I selected, let's graph z as a function of x and y, and then I graphed z equals 0 and z equals x for the same domain that I had right here. And z equals x is this blue plane, and z equals 0 is obviously the one that's in the xy plane. Okay, it's a little bit, I'm still having trouble with my mouse here, but I hope you can better understand what this thing looks like now. I want to get it back to that same angle, but it's really hard to get it to the angle that I want. Okay, so our surface is actually this surface right here. That's it. It's the part of the cylinder that is in between the xy plane and the plane z equals x. So that's S. That's what we are integrating over here. So now let's actually integrate over this. Now, whenever you're evaluating a surface integral, you have options. You have the surface integral of a function of 3 variables. That's a scalar function. There are actually 3 ways that you can do this. But all of them involve taking a projection on to one of the planes, either the xy plane or the yz plane or the xz plane, because our surface is 2-dimensional. But we'd like to get, in order to evaluate the integral, we need to get everything in terms of 2 variables instead of thinking of it as, or instead of thinking of this function as being multiplied by this little surface area piece for each part of the surface. So here's the first option. We can write this way in terms of x and y only. That's what we typically do. So we write our function not in terms of x, y, and z, but we say, let's write it in terms of x and y, and then replace z with whatever z is in terms of x and y on our surface, and then multiply by the surface area piece. If z is a function of x and y, the surface area is the square root of 1 plus the partial of z with respect to x squared plus the partial of z with respect to y squared. We derived that earlier. And then we would project, we're projecting the surface onto the xy plane because we have everything in terms of xy here. So that's one option, and that's the option that we use most of the time. But that's not an appropriate option here, because if I look at the projection of this cylinder onto the xy plane, I just end up with a curve. I don't even end up with a region to integrate over. So this isn't going to work this time because our surface has an equation x squared plus y squared equals 36. It doesn't depend on z at all. There is no expression for z in that equation, and the projection onto the xy plane is just a curve rather than a region. So we can't do that, but we could just as easily project onto other planes. So rather than projecting onto the xy plane and evaluating this as an integral or a double integral where dA is dx times dy or dy times dx, we could do this instead. Maybe y can be written as a function of x and z. Because it's really arbitrary, really, what letters we call, x, y, and z. We're accustomed to thinking of the z-axis is pointing straight up, but we could easily relabel all the variables and it would just sort of orient the surface differently. So we could write our function or integrand in terms of x and z only by leaving x as x, leaving z as z, and replacing y with a function of x and z. In that case, the surface area piece would be this. Since y is a function of x and z, we would take the partial of y with respect to x and the partial of y with respect to z and substitute those into our surface area formula. And this is where R2, that's our region that we're integrating over, is the projection of our surface onto the xz plane. Because all of these, after we replace y with this function of x and z, and we compute the partial derivative of y with respect to x and with respect to z, all of these are functions of x and z. So we are projecting onto the xz plane and integrating over there instead. And then of course, the third option is this. We could write z as a function of x and y and write everything in terms of x and y. We could write y as a function of x and z and write everything in terms of x and z. Or we could write x as a function of y and z. So we could write our entire integral in terms of y and z. And then the surface area piece would be this. Since x depends on y and z, we're going to have a partial of x with respect to y and a partial of x with respect to z. And then we'll integrate over the region R3, where R3 is the projection of S onto the YZ plane. Now the projection onto the XY plane is just a curve, so we don't want to do that. We want an actual region to integrate over. So we need to think about the projection of this onto the XZ plane or the YZ plane. And I'm actually really close to drawing that projection onto the XZ plane right here. Z is between 0 and X, that's what it would look like. And X is between 0 and 6. So I think our region would look like this in the XZ plane. So that would be for this second integral. If we wanted, we could write this entire integral in terms of x and z and then integrate over this region R2. That's one option. And the third option is to integrate over the projection of this surface onto the YZ plane. I think that's actually our best bet in this case. Now, sometimes when you're looking at these equations, it's hard to see what that projection onto the YZ plane might be. I want to show you in Calc Plot 3D what that projection looks like, and then I want to justify it algebraically. So let's do that now. Okay, so this is our surface. Now, if I'm projecting onto the YZ plane, can you tell? I'm trying to make it straight up and down. Can you tell that that's a semicircle? I don't know if it's obvious that it's a semicircle, but it is a semicircle. We're imagining taking this piece of the surface and then removing that third dimension and just projecting onto the YZ plane, and it looks like a semicircle to me. So I think it's going to be a semicircle. then if we project onto the XZ plane, as I was saying, we're going to see a triangle. It's that triangle right there. Sorry, it's tilted, but I'm having trouble orienting the axis in the way I want. So that would be our region of integration there, because that's the part of the surface that we're talking about. And then again, the projection onto the XY plane is a projection of this cylinder onto the XY plane. It's just going to be a curve rather than something 2D, so we don't want to do that. Okay, so I think the best bet is to project onto the XY plane, or sorry, the YZ plane. And that's going to look like this. Now remember, x squared plus y squared is equal to 36 here. If I project onto the YZ plane, here's my y-axis, here's my z-axis. Now we're going to start at z equals 0 because we know that z goes from 0 to x. But since x squared plus y squared is equal to 36, and z is going from 0 to x, when z is equal to x, we're going to have z squared plus y squared equals 36. That's that boundary, because z is equal to x on that plane. So we'll have z squared plus y squared equals 36, and y is going to range from -6 to 6. And of course, we could solve that for z if we wanted to. We'd have z equals the positive square root of 36 minus y squared. And it's a positive square root because we know that z is positive for this part here. And then if I wanted to describe this region, the easiest way to do it would be to let y go from -6 to 6. So y goes from a constant to a constant. And z goes from a function to a function. Z goes from 0, that's on the y-axis there, up to this semicircle, which has the equation z equals the square root of 36 minus y squared. Now, you also have the option of thinking of this in polar coordinates, and here y would be playing the role of x and z would be playing the role of y. So you could say that y is equal to r cosine theta and z is equal to r sine theta, and dy dz is equal to r dr d theta. I mean, you could do all of that. But I've already looked at this problem, and it turns out that due to the nature of the integrand, keeping this in rectangular coordinates is actually going to be easier than switching to polar coordinates, as we'll see when we set everything up. Okay, so we are going to evaluate this surface integral by doing this. We know that f of x, y, z is x squared plus y squared plus z squared. So we're evaluating the surface integral of x squared plus y squared plus z squared over s. And then rather than doing that, we're going to say that is actually equal to this. And we're going to choose this second one. Oops, just kidding. We're going to choose the third one because I want to project onto the YZ plane, not the XY plane. So that's my plan. I'm going to write the integrand in terms of y and z only. Then I'm thinking of x as a function of y and z. So this will be my surface area piece. And my region R3 is actually that region right there. So let's do it. Oops, it's not a triple integral, it's a double integral. This is a double integral over s of x squared plus y squared plus z squared ds. And basically we need three things. We need a description of the region R that we're integrating over. We need the integrand in terms of y and z only, and we need the surface area. Well, if we're on our surface, x squared plus y squared is equal to 36 whenever we're on that surface there. So the easiest way to get rid of x and write this in terms of y and z only is to replace x squared plus y squared with 36, because x squared plus y squared is 36 when we're on our surface. So we'll have 36 plus z squared here. Now here and here, we need the partial derivatives of x with respect to y and z. And this dA over here will be, well, if I'm writing everything in terms of y and z, that's going to be a dy dz, or you can do dz dy, either one is fine. So I've got x squared plus y squared equals 36. In order to find the partial of x with respect to y and the partial of x with respect to z, I need to solve for x. So I'll have 36 minus y squared, and then I'll take the square root, or raise it to the 1/2 power, same thing. So that's getting me an x by itself. And that's appropriate since x is greater than or equal to 0. So x is between 0 and 6. So we've got that. And now if I want the partial of x with respect to z, it's really easy. There are no z's in this, so we just get a 0. And if I want the partial of x with respect to y, I'll get 1/2 of my inside function to the negative 1/2 times the derivative of the inside by the chain rule, which is negative 2y. The 1/2 and the 2 reduce, and we end up with a negative y over the square root of 36 minus y squared. Right there. Okay, so we're going to square this, probably get a common denominator, and then we need a description for the region R, and then we'll be all set. So my ds is this, 1 plus negative y over the square root of 36 minus y squared, quantity squared plus 0 squared. And this will be dy dz or dz dy, either one is fine. Now when I square this fraction, I can just square the numerator and square the denominator separately. Then over here, this 1 needs to be written differently so that I can add it to this. I would like a common denominator. So I'll write 1 as this 36 minus y squared over itself. So that's the same as 1. And then when I add those together, I can add the numerators, and we'll have the square root of 36 over the square root of 36 minus y squared. And we're still going to have that dA, where dA is dy dz or dz dy. And then we've already described the region R3. There are 2 ways to do it, but I actually like the way I've already listed best. I'd like to let y go from a constant to a constant and let z go from a function to a function. We could do it the other way. We could let y go from a function to a function and let z go from 0 to 6, but I think it's easier if we do it this way. Let's let y go from negative 6 to 6, then z starts at 0 and ends at the equation of this semicircle where z is written as a function of y. So this is z equals the positive square root of 36 minus y squared. Those are our bounds. Since z has bounds that depend on y, we need to integrate with respect to z before we integrate with respect to y. So this is what we have. The double integral over R3 is the integral from negative 6 to 6 of the integral from 0 to the square root of 36 minus y squared of our original integrand in terms of y and z only, which ended up being 36 plus z squared. And then we're multiplying by this surface area piece, which is 6 over the square root of 36 minus y squared. And then these bounds are bounds for z, and these bounds are bounds for y. Now, technically, this is an improper integral because we're going to have problems when y is equal to negative 6 or 6, because then we will be dividing by 0. But actually, the problem sort of disappears after we integrate with respect to z, as you'll see. So I'm not going to worry about it being an improper integral, although technically we probably should handle it that way. All of the limits are finite, so it works out just fine. You can do it that way if you want to. I think I'm going to skip that this time but you should take note of the fact that this integrand is undefined at the end points of this, this outside integral. Okay, so if I'm integrating with respect to z, that's what we always do first. We do the inside first and work our way out. This 6 over the square root of 36 minus y squared is a constant. So I will just write that down. And then I'm anti-differentiating this with respect to z. So I've got 36z. Antiderivative of a constant is a constant times the variable. And then we add 1 to that exponent and divide by the new exponent. And we evaluate from z equals 0 to z equals the positive square root of 36 minus y squared. And again, this is f in terms of y and z. It happens to not explicitly depend on y. Then we have our surface area in terms of y and z. And then we have a description of R3. We've got appropriate bounds. So after you substitute, then you do what we just did, anti-differentiate with respect to z. Okay. Now, when z is equal to the positive square root of 36 minus y squared, we're going to have some cancellations with what we have here, which is why the sort of problem where we're dividing by 0 seems to disappear. Even though technically it doesn't, but it's okay. We can treat it as if it does, because in a limiting sense, it actually does go away like this. So you've got 6 over the square root of 36 minus y squared. And then at my upper bound, I'll have 36 times the square root of 36 minus y squared plus 1/3 times the square root of 36 minus y squared cubed. If you want, you can factor out that 6. It's not necessary, but you can. Then if we split this into 2 fractions, you're going to have 36 over the square root of 36 minus y squared over the square root of 36 minus y squared plus 1/3. And then this is the square root of 36 minus y squared cubed over the square root of 36 minus y squared. You're doing all of that with respect to y. And these guys reduce. And one of these will reduce with one of those. That will make that a 2. And so we just get 36 here plus 1/3 of this the square root squared. So that's going to give us just the radicand, 36 minus y squared. If you want, you can distribute the 1/3. 1/3 times 36 is 12. 12 plus 36 is 48. So we'll have the integral of 48 minus 1/3 y squared. And we're integrating with respect to y. And this is very simple Calc 1 stuff. The antiderivative of a constant, the constant times y, bring the constant down, add 1 to the exponent, divide by the new exponent. You can substitute in -6 and 6 if you want to. Notice that this is an odd function. So if I evaluate this at -6 and I evaluate this at +6 and I subtract them, I'm actually going to get the same thing twice. Now, if you're not with me there, you can always just plug in 6 and -6. But you see, if you distribute that negative, that would make that a positive there, and that would make that a positive. And so we end up with this and this. Well, those are the same. So I would have 12 times 48 times 6 minus 6 cubed over 9. And if I use my calculator to do that arithmetic, this is what I get. 48 times 6 minus 6 cubed divided by 9 times 12. and I get 3,168. Okay, so that was a little bit messy, but I hope you understand the idea. You just replace the integrand with f of x, y, z, and then you have to get this surface area piece written in terms of two variables, and you need your integrand written in terms of two variables. You actually have three options. You can project onto the xy plane, the xz plane, or the yz plane. When we did that, we actually only had two options that would work. Projecting onto the xy plane led to a curve, not a region, so that was out. But the projection onto the xz plane led to a triangular region. The projection onto the yz plane led to this semicircular region. I chose to project onto the semicircular region. And then the way we handle that is we write the integrand in terms of the two variables, which in this case were y and z. X squared plus y squared was 36 on our cylinder, and that cylinder, or part of that cylinder, was our surface. And then we compute ds, which is the square root of 1 plus a partial derivative squared plus a different partial derivative squared. And these are the partial derivatives of whatever function you're writing in terms of the other two variables. Since this is x being written as a function of y and z, I needed the partial of x with respect to y here and the partial of x with respect to z here. After you do that, this is what you are integrating, and you're integrating over the region R3, which is right here. So we've got to do a little algebra, simplify our surface area piece, and then you just substitute. You've got your integrand in terms of your new variables. You've got your surface area in terms of the new variables. You've got to describe your region, letting one of your variables go from a constant to a constant and letting the other one go from a function to a function. And then once you do that, you just anti-differentiate with respect to the first variable and then use the fundamental theorem of calculus. And then you anti-differentiate, well, first we had to simplify. Messy today, we're doing a lot of scribbling today. And then after we simplify, we anti-differentiate with respect to the second variable. And then we use the fundamental theorem. Now we could have just as easily projected onto the xz plane instead of the yz plane, but I think the arithmetic is actually easier in the yz plane because we had that semicircle and the surface area piece kind of looked like this. When the surface area piece looks like this and we're in the xz plane, it's very similar to that. I think we can't avoid dealing with the improper integral. But because we have a semicircular region in the YZ plane, there were some nice cancellations when we integrated with respect to Z first. So I hope that helps. See you next time.